So it is now full screen. Is it visible?
Yes, it is visible.
Okay, so let me know when everyone is ready.
Yes, sir. You can start.
Okay, you can start. Yeah.
Okay. Well, let me first, good afternoon, everyone. And let me thank the organizers for giving me this opportunity to give a talk. The title is Simulating Source Region Dynamics of Solar Coronal Transients, Progress and Challenges. And here, so these are my collaborators. Actually, most of the work is done by them. I am kind of presenting. And as already has been introduced by the chairperson, that I'm Ramit. I work in Udaipur Solar Observatory. We have a small group. We do numerical simulation of mostly coronal transients. So a brief outline, whatever the fancy title says, the source region dynamics is in general believed to be governed by the magnetic reconnection. So I will be focusing a lot on magnetic reconnection. And to understand that magnetic reconnection, we need to understand different coronal models, the way we uh, construct coronal magnetic field lines. So there are potential, linear force-free, then there are non-force-free coronal models, which I will briefly touch upon, the theory and mathematics, and go to the application. Now in the application, you will see that with these coronal magnetic field lines, once constructed, can either be used for morphological studies. By morphological, I mean what is the shape, how the magnetic, what is the magnetic helicity, what is the twist, such kind of studies, which are basically static studies. There is no dynamics involved. And the other is numerical simulations, where you use these um, extrapolated field lines, which are constructed from the photospheric magnetograms. They are used as an input to MHD simulations. And then we kind of try to study how the magnetic reconnection takes place. So there are two ways of doing numerical simulations even. Both have their own challenges. The first one is obviously from the first principle, where the initial state is purely analytical and it is not derived from the vector magnetogram. And the other one, where I'm going to focus more, is the data constraint or data driven simulations, where we actually extrapolate photospheric data, then put that into the simulation and see how it evolves. And obviously, I will try to summarize the whole talk. So these are some very basic parameters of solar corona. So this is like bringing coal to Newcastle, but they have very important impact. So I'm kind of going through it. The temperature, is of the order of million degree Kelvin. Eta is the magnetic diffusivity. B varies from 10 to 100 Gauss in the corona. And with a length scale of the order of 10 to 100 megameter or higher, and an Alvan speed of 1000 kilometer per second, the corona is actually characterized by a very high Lundquist number of the order of 10 to the power 30. And at this high Lundquist number, the dynamics of the plasma can be described by the non-dissipative limit of MHD, magnetohydrodynamics. And in the non-dissipative limit, the speciality is that the magnetic field lines, they are kind of tied to the fluid parcels, which we call Alvan's theorem of flux freezing. So whenever you push a plasma parcel, the magnetic field line gets deformed because they are tied. And this deformation from Ampere's law J is equal to curl B generates further current. And the whole system kind of evolves in time. So this is what we define as large scales, because unless L is large, this flux freezing condition is not valid. And with such L, if you calculate the diffusion time scale for coronal magnetic field, it comes out to be of the order of million years. Okay. But eventually we do see coronal transients, and as I said that they are kind of manifestations of magnetic reconnection, which is the diffusive limit of MHD. So we need either an increase in eta, or generally some of us believe that the length scale over which the magnetic field varies, it decreases, shortens, and this local reduction in length scale actually can be realized by current sheets, neutral points, 3D nulls, and possibly quasi-separatrix layers. So before we get into that, let me give you some example of coronal transients. All right, so these are very well-known things. So the first thing you please note is that there is a eruption. This one is a CME actually, and the dark material is the filament which ejects out. And this filament is basically confined plasma, and to confine the plasma, we need a magnetic bottle. So it is kind of a helical magnetic field line anchored on the photosphere, which confines this plasma. These are called magnetic flux ropes, and they play a crucial role when it comes to eruptive events or any coronal transient. On the right hand side, there is a figure which shows a coronal jet and a classic two ribbon flare. So just wait and you can see the two ribbons forming, and on the right hand side there is a jet, okay, which is a collimated beam of plasma, and in this particular case we were able to identify the spire. So we thought we kind of confirmed it as a blowout jet, and I will talk more on this. So this is something which I asked yesterday also. This is a sorry, yeah, okay, okay. I know how to play this movie. I have to give up the pointer. So there's no laser pointer, and here you can see this is a movie of coronal rain, and practically you can see this is like a 3D null kind of morphology, but I'm still writing a probable candidate because we are not sure. Here also it looks like a 3D null. You can see, you can identify the spine here and the dome kind of structures there, but yet no such studies has been done where no such simulations are at least done where this kind of coronal rain are kind of proposed as coronal transients. But as I said that all these transients, there's a almost a general agreement that they are due to magnetic reconnection. And this is a nice cartoon from Wikipedia actually. So you can see by magnetic reconnection, the most general definition of magnetic reconnection is that a phenomena in which the magnetic field lines, they change their connectivity. So if you see, I don't know whether these are visible or not, there are two dotted dashed lines, and there are field lines on two sides of the dashed lines which are connecting two different regions. So on one side, a field line starting from here connects this region, but on this side, the field line connects this region. But that changes when these two field lines meet and reconnect at the central point, which is a X-type neutral point. Neutral point, by neutral point, I mean point where magnetic field is 0. So these are two-dimensional reconnections, and two-dimensional reconnections are well understood. But as we move on into the presentation, you will see that it is not very often you see two-dimensional reconnections. Mostly it is three-dimensional reconnections that you see, which is still a very open subject. Sorry, for the research. So before we get into this whole business of uh, studying the source region dynamics, let me say a few words about how the coronal magnetic field is constructed. The idea is that the corona, the global corona, is kind of considered to be in an equilibrium. It's a quiescent corona, so that you can neglect the acceleration term. This is simply Newton's law. You have acceleration on the left hand side, and on the right hand side, you have all the forces. So P is the kinetic pressure, J cross B is the Lorentz force, and rho G is obviously the gravity. Now, at the coronal height, the rho G does not matter much. One can show that. So the amplitude is very small, and the only two possible dominant players can be either the kinetic pressure or the Lorentz force. Now it turns out that from this famous diagram, okay, from Gary 2001, it turns out in the mid corona. So I'm not talking about photosphere. Please see at the photospheric level, this plasma beta, which is the ratio of plasma pressure or kinetic pressure to the Lorentz force, okay, that is larger than 1, so plasma pressure dominates. But at the mid corona, the plasma pressure or the kinetic pressure is very small and can be neglected over the Lorentz force, J cross B. So J cross B is equal to 0 defines the coronal magnetic field, where J is the volume current density. Now, this term can also be written in two parts. One is the magnetic tension, which is the left hand side. The other looks like a pressure term because it is gradient of B square by 2. This is called a magnetic pressure. So in standard terminology, we say that the coronal field is basically force free, where the force free condition is achieved because the tension force gets balanced by the magnetic pressure. Now we look for the solution of this J cross B equal to 0 equation. The obvious solution is the trivial one, B equal to 0, which certainly we are not going to take. But there is one more solution, which is the current itself is 0. So J is equal to 0. So the magnetic field is basically potential. And as I'm going to show that a current free field, particularly if there is no component of current aligned along the magnetic field, then the magnetic field lines are untwisted, and hence this potential magnetic field gives you untwisted magnetic field, and you can apply it only for the quiescent corona, not for the active region corona, where the potential, where the magnetic field lines are heavily twisted, structured, and complex. The other way, the other solution is obviously J is parallel to B, because then also J cross B is 0, and the easiest solution is J is equal to a constant alpha naught times B. And please note that this alpha naught represents the twist actually of the field line. And alpha naught being constant, the twist is constant throughout the region of interest. But observationally, we once again see that that is not the case, because different field lines can have different twists. So this is called a linear force-free field. Although it is analytically solvable, but there are other issues like constant twist, and there is another issue of energy. So people looked for a general alpha which is a special function of space, is a special function. It varies with r. So they wrote J is equal to alpha r. R is a position vector multiplied by magnetic field B. And then this cannot be the only equation, because one has to satisfy the condition of solenoidality in magnetic field, divergence of B has to be 0, which gives you the second condition, grad alpha dot B is equal to 0, which means that alpha, although can vary over the volume, but has to remain constant along a magnetic field line. So this is a very stringent condition actually. But this is the standard model that we apply to understand active or to construct magnetic field lines in the active or layering regions. So a bit mathematics, the potential field extrapolation actually relies on B is equal to writing grad psi. Psi is the magnetostatic potential, and divergence of B equal to 0 gives you a Laplace equation, and which can be solved with periodic boundary condition. And as soon as I say periodic boundary condition, you can see that the challenges I am already in, because the photosphere is not periodic. If you look at active region, the magnetic field lines are twisting, turning, twirling. They are doing everything, but they remain periodic. But nevertheless, this is an approximation, and the simplicity of this approach is that only line of sight magnetic field is required, okay, to construct the or to extrapolate the magnetic field. I'm not getting into the details of the calculation, but F represents a Fourier transform here. So the next one is the linear force-free extrapolation. I'm concentrating on linear force-free because this can be analytically solved. Non-linear cannot be. So the idea is once again to write B in terms of a poloidal and a toroidal flux function. Poloidal field and a toroidal field, poloidal flux function and a toroidal field rather. And this is, although this is done in Cartesian coordinate, but one can solve it in every other coordinates also, coordinates where Laplace equation can be separable. So this, when substituted into the curl B equal to alpha B, gives you a Helmholtz equation, sorry, not Laplace equation, but a Helmholtz equation in this case, where T is chosen to be alpha into T. The idea is, if you try to solve this Laplace equation, the Helmholtz equation, assuming a solution like this one, okay, where the magnetic field falls off with height, you will see that the solution has a psi, which is something into e to the power minus square root of e to the power minus KLM Z. So now the idea is that because as you are going away from the source, the magnetic field has to decay, and so KLM has to be a real quantity. So this alpha, which is a twist parameter, that cannot be more than the K. Okay, K is the mode number in the Z direction. So this linear force-free extrapolation is actually limited by the fact that there is a upper limit of twist. You cannot model field lines which are more than having a twist, more than having this upper limit of twist, more than having this threshold value.
Ramit, 20 minutes are over.
Yeah. So then there is this non-force-free simulation, non-force-free extrapolation techniques also. So I won't get into the details again, but the idea is that you solve a hierarchical equation where two of the field lines, two of the magnetic field, superposing magnetic fields are linear force field, and another is potential. And this is a very general scenario because it falls off very fast, all right, with height, and the Lorentz force almost becomes zero, whereas in the nonlinear force field, the photosphere is also force free, which is not the case. So this is a slide I think I can skip here because of the time constraint. This just shows that a simulation from first principle where you can see that magnetic field lines. So this is they come toward each other, they get reconnected and generate a flux rope, which when goes up stretches the overlying or the strapping field lines. And if the torus instability condition is satisfied, then it can yield a CME, otherwise not. Okay. But unfortunately, the things are much more complex. When you extrapolate magnetic field, this is an actual extrapolation using the non-force free, and you can see the magnetograms. I think this is the original magnetogram, this is extrapolated magnetogram, they match very well. And here we saw that the flux ropes are not at all ideally what they used to look like in the previous one. All right. So these two small yellow colored things, yellow colored twisted field lines, they constitute a flux rope. And there is a three-dimensional magnetic null at this point. So this is a location particularly at which magnetic field is zero. And as reconnection takes place at this point, this is a simulation result. Then the overlying field lines, they kind of go away from their position. And as the magnetic field lines move away because of reconnection, the magnetic pressure decreases and the flux rope starts to rise. Okay. So things can be pretty complex, and but it is not always that you will find a flux rope in an eruption. This one yielded a CME because once again it had a flux rope. This is another simulation which you can see that this is the event. There was a circular flare ribbon and there was a magnetic null when we extrapolated. It was located here. And you can see as the reconnection takes place in the magnetic null, the overlying field lines actually go up, but since they do not meet the, but since the rope is absent, I believe, there was a failed eruption. Okay. And also the torus instability criteria was not met. So loose, which is very loosely speaking, and if asked, I will explain why I'm saying this is a very loose statement. But the simulation is quite okay because you can see that the fingering kind of motion, the slipping kind of motion that you see here at the bottom is also can be monitored in the observation. So in the last example, I'm going to show you the jet, coronal jet, actually the jet part. And here the jet will appear once again. Just yeah, the flare here is the jet, and then we once again extrapolated. These are the extrapolated field lines using the non-force free technique. Once again, they agree quite well. At least, and we calculate the Pearson correlation also. It's not that they agree well in visibly, but also quantitatively. And here is the simulation. You can see that there is a small flux rope in yellow color, marked in yellow color, which is a twisted field line. And there is a 3D null located over here. And when the reconnection starts, the flow develops exactly along the ambient field line. So these green colored arrows are flows. They kind of start to get aligned along the red colored field lines, which form the spine of the thing, spine of the this particular 3D null. The 3D null is located here and gives rise to the jet. So, and this is actually an inner reconnection which is happening below the jet. I won't talk much about it, but you can see development of a X-type neutral point over here. So X-type neutral points can also be observed in a three-dimensional reconnection. That was my point. So the challenges are basically here that how good these extrapolations are. One needs a multi-wavelength observation to identify different structures, then tally the structures with the simulations and get very deep into it to understand how the dynamics takes place. But still we do not know what triggers this dynamics. In our case, it is an unbalanced Lorentz force, but really we don't know that what is happening in the sun. So that is a question that we need to look for. So with that, let me come to the end of my presentation. So I have presented the current understanding of coronal magnetic field modeling. Fundamentals of force-free, non-force-free models are discussed. The concept of data constraint simulations presented, examples are discussed. I have highlighted non-force-free field extrapolation because we do it over here, but equally well in other groups, other areas, other countries, people use nonlinear extrapolation techniques also. Both MHD simulations from first principle and data constraint are introduced and demonstrated, and both are actually very much required to understand what is going on. Okay, and this whole package can be used for the Aditya science goals to achieve Aditya science goals, as well as for any other space-based or earth-based observations. So thank you very much.
Thank you, Ramit, for a very nice presentation. Now the floor is open for questions. Please raise your hand. I don't see any raised hand. Is there anyone in the lecture hall that who wants to ask a question? I can't hear the voice.
Well, there is no question in house persons only, but I don't see any online persons also, so we can move forward.
Okay.
If I hear correctly, there is no one is asking question in the
Yes.
lecture hall. Okay. So on the Zoom panel, yes, there is one. Go ahead.
Okay.
Hello. So so very nice talk. I'm Wagi. So actually, I wanted to know that with this simulation, can we see the early dynamics of flux slope, and can that be compared with VLC observation, Aditya observation?
Yeah. So yeah, you can do that, but yes. So one can do that, but not with this particular set of because this one uses a Cartesian geometry. So we are developing a spherical polar geometry extrapolation model because your Aditya L1 VLC is going to give me the BR B theta B phi, I think, two directions and one magnitude. So that is in progress, and once it is done, obviously we are going to track the early evolution of CMEs.
Okay, yes. Okay, I think
So that is one of the objective actually.
okay. Yeah, so because I was interested to see if we can compare and then see the reliability of such models, because most of the time tracking the early evolution is very difficult in most of the models which I
Yeah, mostly not the reliability. I would rather say that how the dynamics develops during the onset of a CME, what triggers the reconnection, things like that.
Yeah, okay, thank you.
Thank you. So I think there are no more questions. So we thank Ramit. And now I request the second speaker, Kartika Sangal, to share her screen. And hello, you are muted. Do you have to allow her?
She is in person.
Slides.
I still can't hear.
Yeah, I'm audible.
Yes,
Okay.
thank you. So you can start your presentation now.
So good afternoon, everyone. I'm Kartika Sangal, a research scholar working with Dr. Srivastava at IIT BHU. First of all, I would like to thank all the organizers for giving me this opportunity to present my work here. And the title of my talk is The Study of the Transition Region Oscillations in the Quiet Sun as Seen by Iris. So in today's talk, I will be presenting the in today's talk, I will be discussing the result of my recent work. We have analyzed transition region oscillation in the quiet sun using iris data in sit and stare mode. So for this work, we have used Silicon line. We have used Silicon 1393.77 angstrom line. It is an optical thin line and has a Gaussian shape. So first, we have derived spectral parameters, that is intensity, Doppler velocity, and line width. Then after we have derived time distance map that has been shown in the figure. Now the bright patches that has been shown in the intensity images are the network region where magnetic field is strong, and the dark patches that are shown in the intensity images are the internetwork region where magnetic field is weak. So in our work, we have analyzed oscillations of intensity and velocity in both bright and dark region. And the selected bright and dark region are shown in the figure. And for this work, we have used wavelet analysis tool. So first, I would like to tell about what is wavelet transformation. Wavelet transformation is the convolution of the time series with the mother function. And we have used Morley function as a mother function. And Morley function is given as gi naught eta is equal to pi to the power minus 1/4 e to the power I omega eta e to the power minus eta by 2. Basically, Morley function is a plane wave modulated by a Gaussian function. Now the power of a wavelet transformation is defined as square of the absolute magnitude of a wavelet transform. Like in this example, in the lower panel, you can see the power spectrum of intensity in panel C and the power spectrum of Doppler velocity in panel F. Now the most crucial step in the wavelet transformation is to ensure the reliability of the wave period that are detected through wavelet analysis. And this can be done with the estimation of the confidence level. And for the confidence level, and the confidence level can be estimated and the confidence level can be estimated with the help of assumed background model. So in the wavelet analysis, there are some background models like white noise model, red noise models that has been proposed by Torrance and Compo and that are widely used. But we did not use this model. In fact, we have used power law model that has been proposed by Ojari 2016. So what Ojari has proposed, he has proposed the power law behavior of UV and EUV time series, and he has proposed a power law model for the same. So we have used this equation sigma V is equal to A mu S plus C. So what we have done, we have fitted the FFT of the time series with this equation. Then after fitting the fitted array that we have got, we have taken this fitted array as the background model, and then we have estimated the confidence level. So moving. Yeah, it is working. Thank you. So this is the example of wavelet analysis in a bright location. In the upper panel, shows the time series of intensity and velocity. See, in the middle panel B, the black curve is the FFT of the time series, and the red curve is the global wavelet power, which is defined as time average of the wavelet power. So, like I have already told, we have fitted this FFT with the power law equation. Then we have got this blue curve. This blue curve is the fitted curve, and with the help of this fitted curve, we have calculated the confidence level, and the confidence level are shown in yellow and green color. Now in the panel C and F, the panel C and F shows the wavelet, shows the intensity and velocity power spectrum. So the panel C is corresponding to intensity wavelet spectrum. Here the dominant power lies within 8 to 16 minutes, while in the velocity, the dominant power lies within 4 to 9 minutes. And you can see the blue contour here. The blue contours are the significant contour, and this is very important. Like in the wavelet analysis, we can say if the power lies within the significant contour, then only the power is considered as significant, and the period corresponding to these significant power are considered reliable. So this is very important to estimate these significant contour. Like in the right panel shows the example from a dark location. Like in the figure C, this is the intensity wavelet spectrum at a dark region. Like at around 32 minutes, the power is quite dominant, but we will not consider this power as significant one due to two reasons. The first reason is this power does not encloses within the significant contour, and the second one, the power is lying in this crossed hash region. So in the wavelet analysis, if the power lies within this crossed hash region, we will neglect this power. So what we have done, we have applied some conditions to extract the reliable period of intensity and velocity signal. And what are these conditions? The first condition is only significant power is taken. That means the power that lies within the significant contour is taken. And the second condition is the power outside COI is taken. That like in this example, in this intensity power spectrum in a dark region, the dominant power that lies within the COI we do not consider this power. After that, we have plotted the statistical distribution of period in velocity. We have plotted the statistical distribution of intensity and velocity signals in both bright and dark region. And panel A is the distribution of period of intensity in bright region. Panel B is the distribution of period of velocity in a bright region, and panel C and D are corresponding to dark region. So after that, we have computed the mean period, and what we have found, the mean period in both regions, bright and dark, the mean period in velocity and the mean period in intensity are consistent with each other within 1 sigma value. Like you have seen, in the bright region, the mean period in intensity is around 7 minutes, and the mean period in velocity is 8 minutes. And we have 1 sigma value which is 3.95 minutes. So we see that both are consistent with each other within 1 sigma error. Similarly, in dark region, we have mean period in intensity is 7 minutes, and we have mean period in velocity is 5 minutes. So till that, we have analyzed oscillation in bright and dark region. After that, we have also computed the phase difference between intensity and velocity signal to understand the physical nature of these waves. So for this, we have used cross power wavelet coherence in our work. So what is cross power? So first, I will tell what is cross wavelet. Cross wavelet is the multiple product of intensity wavelet and with a complex conjugate of velocity wavelet. And what is cross wavelet power? Cross wavelet power is the square of the absolute magnitude of the cross wavelet. Like panel B is corresponding to bright region and panel E is corresponding to dark region. After that, we have calculated the wave coherence that has been shown in the figure C and F. Like in this figure, you can also see the blue contour. So these blue contours are the significant contour, and in case of cross power, what we have done, we have first computed the cross FFT, that is the multiple product of FFT of one time series with the FFT of other time series. Then we have fitted the cross FFT with our power law equation that I have explained earlier.
Kartika, 10 minutes are over.
Now again here, to extract the reliable phase difference, we have applied 3 conditions. The first 2 conditions are same, like wavelet, like the cross power should be significant. The second one is region should, the power should lie outside, the power that is lying outside COI is taken. And we have applied another condition, that is the wave coherence should be greater than 0.7. Now these are the distributions. The panel A is corresponding to bright region, and the panel B is corresponding to dark region. So in both region, what we have found 3 peaks. Like in the bright region, the distribution peaks at -119 degree, 33 degree, and 102 degree. While at bright region, the distribution peaks at 153 degree, 6 degree, and 153 degree. So we know in ideal MHD, there is a phase difference of 0 and plus minus pi between intensity and velocity in case of propagating waves, while there is a phase difference of plus minus pi by 2 between I and V in case of standing wave mode. So on that interpretation, we say that there is a variety of slow magnetocaustic waves present in the transition region. Now comes to result and conclusion. So we have analyzed period in 2 different regions, bright and dark region. After that, we have plotted the statistical distribution of intensity and velocity oscillations, and on the basis of mean period, and on the basis of these distribution, we have found the mean period. And in both regions, what we have found, the mean period in velocity and intensity are consistent with each other. After that, we have determined the wave mode on the basis of phase difference. Then on the basis of phase difference, what we infer there is a variety of slow magnetocaustic wave present in the solar transition region. Based on the statistical result, the transition oscillations are attributed to upward and downward propagating slow magnetocaustic wave. In addition, we also found the signature of standing slow waves. So thank you so much.
Thank you. Now the floor is open for questions. Is there any question? You can raise your hand.
Hello, can you hear me?
Yeah, I can hear you.
Yes.
Yeah. Okay. Thank you for a nice talk. Maybe I missed it. What regions are you actually investigating? I mean, what are these bright and dark regions? Are these like active region mass or coronal holes? What
We have
exactly are these?
analyzed oscillation in the quiet sun, right? And in the quiet sun, we have what we have seen in the chromosphere, two kind of region. One is network region and another one is internetwork region. So we have analyzed oscillation in both regions.
Okay, so that means the internetwork region is the one which is bright, right?
No, network
Or-
region is the bright, where magnetic field is strong.
Okay, and internetwork is the one which is dark. Can you go back to your
Yeah, sure.
conclusion slide? Yeah, so now you said that, no, the next one.
Yes.
Yeah, so you find a phase difference of like 150 degree, which is approximately pi.
Which
right?
is approximately
Yeah,
pi.
and
Yeah.
102 degree, which is approximately pi by
90
d.
degrees.
Yeah, so in one region you find like propagating wave, and in other region you find standing waves. I mean,
In
what-
one region, we found both propagating and standing wave in the bright region, and in the dark region, we found only the signature of downward wave.
So why is
Propagating wave. It can be upward or propagating.
okay? But why is it so? I mean, is there a physical reason for this? That why we get only propagating waves in internetwork, right? Because dark vision is your internetwork. Yeah. Anyway, yeah, so.
Yeah, somewhat continuation of this. Now, for the period thing, you were showing the period numbers or values
Yes,
with
sir.
uncertainties.
Yes, sir.
3-4 minute uncertainties. So basically, they are almost the same. Now, intensity, velocity. Similarly, I think you should quote uncertainty in the phase also.
In the phase also, yes, sir.
Because you have a
Yeah, we have quoted that in the paper, in our paper, but I'm not quoted here in the
So
presentation.
when you do the uncertainty in your phase also, you will see probably there's a considerable overlap. So I think you have to worry about this interpretation. Of course, we know network has certain magnetic structures
Yes,
which
sir.
goes further up in the transition region
Transition.
up and so on. But the question what Vayu was trying to drive at, whether there is any significant difference in the magnetic structures in the network and the internetwork. We
Yeah,
expect them to be quite different.
they are
So
quite
we
different.
expect them to be quite different. So the wave properties also should
Or should
have
be different.
some difference.
Yes, sir.
And whether you can identify that difference rather than just saying that you see both probably will be necessary. for
Yes, sir.
final
Yes.
Okay, thank you.
Okay, thank you, sir.
Okay, thank you, Kartika. We now move on to the next talk by Pawan Kumar, again from IIT BHU. How early can we predict the solar cycle strength reliably using the polar precursor method? So I will give you a warning at 10 minutes.
Yeah.
Will
You allow me to share?
You can share, but if you
Allow us.
cost here, so you can share your screen also, but it give us some timeline, then we can share this. This is connected through Wi-Fi. Can you copy?
Actually, my study like a reflex, so see the separate figure.
Okay. I thought you were.
So you can see it from its your post, no?
Is there an issue? We can, if there is an issue, we can.
No, we can.
So good afternoon, everyone. I am Pawan Kumar from IIT BHU.
Come closer to the microphone and speak loudly.
Yeah, from IIT BHU under supervision of Dr. Vidya Vinay Karat. So my work currently now going on the solar cycle prediction 25. So we got some interesting result about cycle 25 and other things. So many people did the solar cycle prediction using different method. So we are predicting the next cycle using polar precursor method. And we know that solar cycle prediction is a very challenging and essential, and because it drives our space weather and it directly affects the human civilization. The polar precursor method is a very well known and verified method by scientific community, and many people did the prediction using a polar precursor method. So here we show a plot which shows the variation with time, which shows the variation with time of sunspot number and polar field of the sun. So from this figure, we can see that when the cycle peak attains maxima, then polar field at about that time attains minima. So using this property, we predicted the next cycle amplitude. So here the black vertical line shows the time of polar field reversal, and using this property of the data, we in our analysis we use as a solar cycle landmarks. Also, this vertical line shows the sunspot area maximum, and this vertical line shows the polar field at solar cycle minima. So in polar precursor method, people did a prediction using a polar field as a seed at the time of the solar cycle minima. So the next cycle amplitude can be predicted using this method about 4 to 5 years before the solar cycle maxima. So if the polar field of n cycle, so the people predicted the n+1 cycle before the 4 to 5 years. So our motivation is that can we predict the next cycle amplitude before the solar cycle minima? And other question is how early can we predict before the solar cycle minima the next cycle amplitude? So we analyze some data, some observational data and some proxies data like WSO data and polar cycle count and AT index data. So since the observational and proxy data are in limited number of amount, so we use some dynamo models. So we have used 3 dynamo models. One is the Surya dynamo model, which is axisymmetric dynamo model, and produces many results which is match the some solar properties. Also stable dynamo models and 2x2D dynamo models. So using this data, here is the data of observational plot, and we have calculated the linear correlation coefficient of a polar field with respect to next cycle amplitude as a function of time. And this plot shows the here the polar field time of polar field reversal, and these other vertical lines which shows the average time from polar field reversal to solar cycle minima. So generally people did the prediction using this polar field data at the solar cycle minima. So after polar field reversal, 5 to 6 years, people did prediction of next cycle. So in this plot, we can see that after some time, the correlation gets saturated, and here we see a plateau-like region for different data. So if we assume 0.8 correlation coefficient as far as a acceptable prediction, so we can predict the next cycle amplitude after 4 years of the polar field reversal, which is 2 to 3 years earlier than solar cycle minima. So from this method, we can predict the next solar cycle amplitude 2 to 3 years from solar cycle minima. So from this method, we have predicted the next cycle amplitude will be 120 plus minus 25. Also, since we have a limited number of data, so we have uses that dynamo model, and in this dynamo model have some different parameters. So all that dynamo models shows some different property, but we only consider the same feature in all dynamo model produces. So in all dynamo models, we can see the plateau-like region. So this model also verify our assumption. After this work, we have explored to more about the solar cycle prediction, and we computed the polar field rise rate with the next cycle amplitude correlation coefficient. This is the observational data plot in which we computed the polar field rise rate correlation with amplitude of the next cycle. Here only 3 points. So there may be some doubt on reliability of this data, but here we get a strong correlation. Also, from the polar field, WSO polar field data, we have calculated the rise rate between 0 to 3 years of different phase of the cycle and average these rates for one rate for each cycle. Here we should noted that we have to consider that average between 0 to 3 years or less time. If we consider the rates after 3 years, so we may not get correct result, because after 3 years polar field will be get saturated. So this idea we also verified by models. So in our models also we get a high correlation. So using this method, we predicted that the cycle 25 amplitude will be 137 plus minus 23. So if we predicted using this method, so we can predict the next cycle amplitude before the 9 years of the solar cycle maximum. After that, we have got a very interesting result that rise rate of the next cycle and rise rate of the polar field also correlated with each other. So we know that the Waldemar effect, that is WE2, rise rate of the cycle directly related to the amplitude of the cycle. So here the polar field rise rate is also related to the rise rate of the polar rise rate of the cycle. So also this link the physical connection between the polar field rise rate and the Waldemar effect. We got this property in both dynamo models and observation data. Also, we have used. We know that the current solar cycle have gone 2 years. So only 2 years for only 2 years of the rising phase of the cycle, we have applied Waldemar effect, that is WE2, and predicted the next cycle amplitude, that is 25, which is would be 138 plus minus 26, and we verified our idea using this model and predicted previous cycle. So in previous cycle we also get a good result which is agrees with observational data. So our conclusion is that we can predict the next cycle amplitude before about 9 years before the solar cycle maximum, and we also here see that a physical link between the polar field rise rate and the Waldemar effect, that is WE2, and we get the next cycle amplitude after 4 years of the polar field reversal will be 120 plus minus 25, and here also we see some prediction of next cycle 25 by different people. So here is the our prediction. Here is the our we did the first 3 prediction did by us, and so our prediction is very close. Said that the cycle 24 is slightly strong. The cycle 25 will be slightly stronger than cycle 24. Thank you.
Thank you, Pawan, and thanks for finishing in time. So we have time for discussion. Please raise your hands if you have questions for Pawan. I don't see any raised hand. Anybody in the lecture hall?
No, I think nobody is seeing it from the.
Okay, so now Pawan, I had a question. You are talking about predicting the solar maximum with the, and you said in the conclusion that you need 3 years before the minimum. What happens when you have a deep solar minimum, which is continuous for several years? So how does it affect your model prediction?
Ma'am, we get the not only model, we get the this result from observational data.
Yeah. So in that case, because you are saying minimum 3 years before the real minimum, because the
Yeah.
minimum itself is too long. So when do you expect it to, use?
We get this result because of the polar field becomes saturated after some time. So for this reason, we get this type of result. Actually, we predicted the cycle amplitude when polar near about the polar field peak, when polar field will be peak. So polar field in some time of range, polar field like a saturated. So for this reason, we get earlier. We can predict earlier using polar field.
Okay, I'll discuss with you later. Thank you very much. Now we
Audience here, ma'am.
sorry.
Yeah, this is Dipankar here. Yeah,
Yes.
Pawan, I think Pawan is not using as a start of the minima as the time t0. So Pawan's thing is all related with the polar reversal.
Yeah, I understood that.
Yeah,
Yes.
so that way it doesn't matter
Where
the minima
when
is
the real minimum is. Okay, yeah. Okay, so thank you, Pawan. We now move on to the next presentation by Ranadeep Sarkar from University of Helsinki. Ranadeep, are you there?
Yes, ma'am. Am I audible?
Yes, you are audible. Please start sharing.
Thank you, everyone. First of all, I would like to thank all the organizers to giving this opportunity to present my work here. So I am Ranadeep. Currently, I am postdoctoral fellow in University of Helsinki. So today I'll be presenting a part of my work, which is a part of the EUHFORIA 2.0 project. So here I'll be basically presenting a set of numerical MHT simulations on realistic CME models, on realistic CME events. And I will introduce how we encountered the spheromak tilting instability there and how does it pose a great challenge for the space weather modeling. So to begin with, I'll give you a brief introduction to the EUHFORIA. It is a physics-based simulation tool designed for the space weather forecasting purposes. So there are two domains. So first, the domains is up to 0.1 AU, where based upon an empirical-based coronal model that provides the all plasma conditions at 0.1 AU, which is the lower boundary for the heliospheric model, and also to study the evolution of a CME flux rope. We constrain a linear force free flux rope model, which is here we widely use the spheromak model as the flux rope, and we constrain the flux rope properties and also the other kinematics of the flux rope from the observations, and we inject it at a 0.1 AU, which is the lower boundary of the heliospheric model, and the rest of the part is taken care of this global MHT model from 0.1 AU to 2 AU. Now, with this model, we studied a real CME event. So for forecasting or to get a realistic space weather forecasting, one need to in particularly for the context of prediction of busy component at 1 AU, it is important to constrain the magnetic parameters of a flux rope at the lower boundary of the model. So first, so from the remote sensing observations, we constrain the flux rope properties, like the magnetic flux of the flux rope was constrained through the observation of the reconnection flux, and also the direction of the axial field, and the geometric properties like the direction of propagation and also the angular width was constrained through the GCS reconstruction by applying it for 3 different viewing angle. And finally, what we got, the flux rope structure is like that. It was northward directed and left-handed twisted. So with that, we constrain the spheromak accordingly. So here we show the configuration of the spheromak when we just inserted. So here I have only plotted the magnetic field lines, which is gyrating along the magnetic axis of the spheromak. So So this is the magnetic axis of the spheromak, and you can see that it is the helicity sign also like the left-handed rule it follows. Now, when we observationally constrain the spheromak axis at the lower boundary of the model, and we try to see the evolution through the global MHD model in EUPHORIA. So when the spheromak reaches at 1U, what we see that the spheromak axis rotates almost like 90 degree, and when it reaches at 1AU, you see the hollow part of the spheromak is along the sun-earth line. So the axis of symmetry is almost rotates like 90 degrees. So I will explain it in detail through some pictorial depiction here. So here you can see there are 3 rows here. So in each row, you see the temporal evolution of the spheromak. So here also for the demonstration purposes, I have only plotted the magnetic field line so that you can pinpoint the magnetic axis only for the spheromak. So all these 3 rows are temporal evolution of the spheromak, but from different viewing angle. So if you look at the first column, so this is the same spheromak viewed from 3 different angles. So in the top row, it shows the angle that is along the sun-earth line. So you are looking along the sun-earth line, and this is the middle panel is on the viewing angle is on the top of the ecliptic plane, and the lower panel it is the side view of the spheromak. So this is the same spheromak viewed from the 3 different angles, and with these arrows you see the temporal evolution. So if you just look at any of the row, so suppose here you see this, the projected axis is aligned almost along the sun-earth line, but as it evolves, you see there is a rotation, so almost like 30 degree kind of rotation, and here the magnetic axis again rotates, and when it reaches at 1U, so the magnetic axis was almost 90 degree when it was as compared to the initial configuration when it was inserted through the lower boundary. So from the other viewing angle also, you can see that initially the configuration was like this, but as it rotates, so when it reaches at 1U, you see the hollow part of the spheromak is basically crossing through the sun-earth line at 1U. So why this is happening? So actually there is a physical reason behind that. So my colleague Eliana Asbestari from our group, so this Asbestari et al, they have found that this is happening due to the spheromak tilting instability. So what is that? When you inject a spheromak in the ambient magnetic field, so there is interaction between the magnetic moment of the spheromak with the ambient field, and the spheromak try to minimize its magnetic potential energy, and it reaches in the stable equilibrium when its axis of symmetry aligns to the radial direction of the magnetic field. So that's the physical reason. That's why a spheromak rotates when you inject it in an ambient magnetic field. So this is a kind of fact that poses a great challenge in modeling any space weather event with spheromak like flux rope, or even not only the spheromak, if you also use the torus model, this fact will be remain there also. So now we have further studied that whether the input parameters of the model has any effect on the spheromak rotation. So motivating from the recent observational studies by Manuela Temer et al. Of 2021, so they have proposed that the CME density at 1AU, it can vary from 10 to the minus 18 to 10 to the minus 17 kg per meter cube. So earlier we were using a default value for the CME for every EUPHORIA run that means until now the work has done on EUPHORIA, so which was 10 to the minus 18. So we so what we did that we varied the within this observational limit the input density, and what we found that with the higher density the rotation is less. So so one order of magnitude higher density is plotted here. So here you can see the magnetic axis of the spheromak. It is almost, if you could just compare this axis with this axis, so the rotation is less in case of higher density. So here through a plot, I have also just tracked how the angle is changing with higher heliocentric distance. So here you can see the maximum rotation occurs close to the sun, like that means within 0.4 or 0.5 AU. So which is quite understandable because the rotation is high when you have the ambient magnetic field strength is also high. So as it goes slow, then the rotation also is less for the higher heliocentric distances. So, but that does not solve the problem, because what we see that when we increase the density, like here I have plotted the north-south component of the magnetic field for the spheromak with the different density values. So you can see that you can separate the two blobs of the spheromak by looking at a north-south component. So, so in this particular case where the density is higher, so you see that the rotation is less in this case because the frontal blob is means when it was launched from the sun, it was this blob was at the front, and when it reaches at 1 AU, still it is at the front of the spheromak. But there is a huge compression that it undergoes huge compression here. So this is a problem regarding the field strength. That means due to this extra compression, you do not get the desired field strength of the CME at 1 AU as compared to what that is expected at there. So here finally I have made a comparison to the in situ and the model results. So with the higher density value we have that we have used here, so we get a pretty decent match with although the BZ arrival is prior to the actual observation, but the arrival speed and the field strength matches quite well here. Although lots of work needs to be done to understand or to tackle the spheromak rotation problem. And just before finishing, I would like to show like our future roadmap to this. Like this is a kind of byproduct of this work where we have found that in a big picture, there is also we can look we can get to see the formation of the sheath regions. You can see, so this is the background images corresponds to the density, and here the background images corresponds to the speed profile. And you see there is a wrapping of magnetic field lines, or in terms of scientific, you can say this is the magnetic field wrapping, which is the one of the main reason for the formation of the magnetic sheets. So that we actually try to see here, but again, to means as we know that magnetic sheets are also one of the important component for the space weather prediction, because a substantial number of major geoeffective geomagnetic storms are caused by the magnetic sheets. But a few, that has not been addressed till now. That means modeling the magnetic sheets and try to predict its space weather impact. So our future plan is to apply the because the challenges are like to means in the MHT we have to go that kind of length scale where we can actually model the sheets. So now with the advancement in the adaptive mesh refinement techniques, we try to apply those in that and try to also model the magnetic sheets for the space weather forecasting purposes. So that's the kind of summary that we have proposed new methods to constrain the magnetic flux of a spheromak. Although I didn't talk about much more on this in this talk due to the time constraint. And we validate this EUHFORIA tool for the CME in 2013 April 11, and we see there is a the existence of the spheromak tilting there. So and we have found that with the higher density the rotation is less, but there comes again the CMEs undergoes a significant compression for that particular cases. And our future work will focus on finding more practical solution to tackle this spheromak rotation problem. So with that, I would like to end here and thank you.
Thank you, Ranadeep, for a very nice presentation. I'm sure there are some questions. Let's see. Please raise your hand.
A lot of hands in the room.
Okay, there are 2 hands raised. Argadeep Paul, please go ahead.
Yeah, Pawan is asking. Go ahead.
Okay.
Yeah, yeah, very nice talk. Thanks. I just one query that how you are constraining this tilt instability from solar surface to 0.1 AU means before the MHD domain.
Okay. So before the MHD domain, there is means you want to say that how I constrain the orientation angle, the tilt angle of the spheromak.
Yeah, yeah.
Yeah. So what we see that from the let me come to this slide. Yeah. So from here we actually estimate the axial direction, but what do you see from the on disk images? That is not the final orientation of the axis. So you then try to look at the orientation angle or the tilt angle from the GCS reconstruction. Although the GCS reconstruction only give you the tilt, but don't give you the axial direction. So combining these two factors, we determine the axial direction. So the GCS tilt is more or less is the axial direction of the magnetic axis of the spheromak that we constant at 0.1 U. And of course that we have the observations of GCS. Let's suppose I constant it at 15 solar radii or 10 solar radii, and I consider that okay, this will be maintained up to 0.1 AU, that means 21 solar radii.
Yeah, okay, thanks. So one more curious question that whether EUHFORIA is going to implement any other technique than spheromak for CME this thing?
Yes. So in EUHFORIA, we are currently implementing the other models also, like there is a model called Fry 3D model and also the Torus model. So we are also experimenting with those models.
Okay, so next question by Vagish Mishra. Vagish, please go ahead.
Yeah, so Randeep, very nice talk. Actually, I have a couple of questions, but I will discuss later. So one question which I want to ask, did you compare the spheromak radius at 1 AU with the observed one? Because this event is also analyzed by us. So there must be some inconsistencies. How much you find that?
The radius of the spheromak at 1 AU, yeah, we can say about from the model. And from the observationally, you want to say the temporal passage or the size of the flux rope at 1 AU means.
We just calculate the size by observation. That may be wrong. We need to use the flux rope fitting model, right? To know.
Yes,
this,
yes.
Right? Did you just try that?
Yeah. So I have not yes, we can obviously compare that from the model. I can.
When we use this event, we found a very large rotation in the tilt angle from sun to earth. So just wanted to get your idea. Okay, thank you.
Okay.
Bhuvan, the last question by Bhuvan.
Ranadeep.
Yes, sir.
Yeah, nice talk. Nice work, Ranadeep. So I'm asking, I mean, out of curiosity, it's not directly related to your presentation. So at the end, you mentioned about the sheet structure and your model, it also, tells about the sheet structure. So I'm just curious to know in how many cases the sheet is responsible for the DST minimum.
I can't, maybe ma'am can say, I can't say the exact number, but I know that that a substantial amount of the geomagnetic storms are driven by the magnetic sheets at 1 AU.
Okay,
Yeah,
okay. So there must be some study, yeah. So if you come across, you can, tell us sometime.
Who's ma'am?
Hello. Yeah, I can give you references, Bhuvan. There are some.
Another question. Who's ma'am?
Who's ma'am? You have to ask him. Okay, so let's move on to the last presentation of this session by Satabdwa Majumdar, a study of volumetric evolution of CMEs and constraints on our present understanding. And he's working at Aries, Nainital. Are you there in the lecture hall, Satabdwa?
Yes, am I audible?
Yes. Yes, shut up. Yeah, we can see your screen.
Not the right presentation.
Oh. How about now? अभी आ रहा है? हाँ. Am I audible?
Yes, please go ahead.
Okay, thank you. Good afternoon, everyone. So I'm Satabdwa from IIA. I'm working with Professor Dipankar Banerjee, and today I'll be talking about some insights that we have developed recently from one of our recent works on how the volume of a CME evolves as the CME is traveling through different heights, and what are the constraints that it brings us to our present understandings. Now, although the basic ideas have already been introduced by the previous speakers, but I'll just briefly touch upon them. So CMEs are again this violent explosions of plasma and magnetic field happening at the solar corona. Most generally, they're defined as discrete bright white light features propagating outwards in the coronagraph field of view, and they're known to show this famous three-part structure in the white light coronagraph images with the leading edge, the cavity, and the core. Also, apart from a scientific point of view, they are also of ample interest from a technological point of view, because they are the drivers of space weather, and they can create huge geomagnetic storms and cause a threat to power grids and satellites and etc. So it's very important that we have a good understanding of their kinematics. Now, one of the most general ways of how CMEs have been understood in the past and in the present is by tracking the CMEs in successive white light images. You track the CME leading edge, and that gives you a height time plot. Once you have that, you can again derive your velocity and acceleration numbers based on derivatives of the height time data. But again, once you are restricting yourselves to measurements on the plane of the sky, you are actually creeping into projection effects into your analysis. Now, also another thing that we are interested in is understanding the behavior of the CMEs in the absolute lower heights in the inner corona. Now, a good number of work in the past have been done in such a way that people have tried to combine extreme ultraviolet observations with white light observations in order to achieve that aim. And once in order to do that, what people have done is, if you combine extreme ultraviolet and white light observations together, you're actually at a risk of compromising the uniqueness of the physical feature that you're tracking in successive images. So the question is, are we at a stage where we can track the CME uniquely in white light observations? And for that, we need white light observations in the absolute lower heights. So as a whole, the major drawbacks that comes along our way for a clear understanding of CME kinematics is, again, the projection effects, and also a lack of good understanding of their kinematics in the absolute lower heights in the lower corona. Now, one of the ways to remove these two degeneracies or these two shortcomings is the one that has been floated by Tharnish et al. 2009, which has also been introduced by Ranadeep in the earlier talk, which is the GCS model, or the graduated cylindrical shell model. On the left, you see a schematic of the model, and this has been widely used in our community. And this is an example where if you fit the GCS generated flux rope to a pair of core 1 observations, and you continue it along the Corto field of view, so you have your 3D evolution of the CME captured from a height of 1.5 to 14 solar radii. So on the right-hand side, you see a generic height time plot, but I would like to draw your attention to this data number on the top, which gives you the first measurement height. So you see that the measurement starts at around 1.7 solar radii. Now, this is good enough for a handful number of CMEs, but again, I must say that there has been a reasonable fraction of CMEs for which the main acceleration phase already gets over by the time the CME reaches this height. So to understand or to capture the total acceleration phase of the CMEs in the even lower heights, we need white light observations again in the lower heights, which is again less than 1.7 solar radii. Also, another drawback that we face often is if you draw your attention to these two particular panels in this table where we have the GCS parameters, often in certain CME orientations, there has been seen that there are degeneracies introduced in some of the parameters based on the orientation of the CME, as observed in the double vantage point observations. And to remove this degeneracy, what is needed is we need another vantage point observations in the form of a third eye. Now, the GCS model has a provision in the form of including LASCO observations along with your stereo pair of observations. But the problem with that is LASCO field of view starts from 2.2 solar radii. So that is again even higher than 1.7 solar radii. So our interest is to capture the evolution in the even lower heights. So the need of the hour is we need white light observations at even lower heights. And also we need a third vantage point observations, again in white light observations, to preserve our uniqueness of the work. And to do that, what we do is we exploit the freedom that has been offered by the GCS model as a form of the third vantage point observations in the form of LASCO. So what we do is we redevelop the code that has been written for LASCO. So we rewrite a similar set of code where we use K-core observations, which is a ground-based coronagraph of MLSO, which offers a fascinating field of view of 1.03 to 3 solar radii. And if we do that, we gave it a fancy name. We call it an extended GCS model because the application has been extended to even lower heights. Now we have the pair of Core 1 observations with the fitted GCS flux slope to it. So you see a Core 1 image and a Core 1B image with the GCS generated flux slope. And now we have the third vantage point, which is a K-core observations of the same CME. Now, as you can see here, we are now in a state where we can track, or we are capable enough to do a 3 vantage point tracking in the lower heights, and that too uniquely in white lights, starting from a height as low as 1.1 solar radii. So another very crucial aspect of this redevelopment of this GCS model is that beyond 2014, so excuse me, what is happening? Is my transition? Yeah, so for the CMEs that have occurred beyond 2014, we don't have stereo B observations because we lost communication with that. And so as a result of that, we don't have observations in the inner corona as a part of the second vantage point. So we were unable to do stereoscopy or 3D study of CME kinematics for CMEs occurring beyond 2014. And now, thanks to this extended GCS model, we now have another eye in the lower heights in the form of K-core observations, and that will again facilitate us to continue doing 3D studies of CMEs for events occurring beyond 2014. Now that the things are in place, now let us see what are the benefits that we could reap. On the left-hand side, you see a generic CME kinematic profile, your height, time, your speed, acceleration, and your width plots. But then again, this plot was generated from the data which is taken by combining Core 1 and Core 2 observations. And now we have our a similar plot, which we derive by taking or including observations of K-core as well. And I would like to draw your attention again to the top panel where you see that the improvement is evident in the first height of measurement. So we have come down from a height of 1.7 solar radii to a height as low as 1.1 or 1.2 solar radii. So this is something which hasn't been done earlier in white light observations, and that too in 3D using stereoscopy. Also, I would like to draw your attention to this yellow shaded region, which demarcates the impulsive phase of the CME. And you can see that we have been able to capture the impulsive phase uniquely in white light observations. So what we can say is we can now do away with our earlier plots. We have a new set of plots where we can study the impulsive phase, not just the impulsive phase. In certain cases, we are good enough to capture the gradual rise phase as well, as you can see on the left-hand side. And now we can capture the 3-phase kinematic profile of CMEs in white light observations, and including the initial first 2 phases, which have been evading our understanding for quite some time. Now, apart from the radial kinematics, as you can see here, a CME as viewed from different points in space looks completely different. On the left-hand side, what we call is an axial perspective of a CME. And on the right-hand side, we see a lateral perspective of a CME. And that again tells you that if you try to understand or try to study the width evolution of a CME, then you'll probably get 2 different results if you track the width along these 2 different images. And to differentiate between these 2 orientation of the CME, we need at least 2 to 3 vantage point observations. And again, thanks to the extended GCS model, we now have 3 vantage point observations to help us distinguish between these 2 orientation of the CME flux slope in the heights as low as 1.1 or 2 solar radii. Now, let us understand in this particular case how the lateral perspective of the CME width changes. So this is again a GCS schematic of how a CME looks at from a lateral perspective. Once we study it, we see that the lateral perspective is solely controlled by the aspect ratio parameter of the CME. And we see that for most of the CMEs, the edge on width is initially increasing very rapidly. The shaded region is again demarcating the role that the K-core observation plays as far as improving our understanding in this regard. So you see that K-core is helping us to capture this initial rapid rise in the edge on width of the CME. But this is again not the true picture. This is not the complete picture, because the CME also increases its width on the other way as well, which we call it as the face-on angle. So if we see the CME as a face-on perspective, you see that this is it looks somewhat like this. And from the cartoon itself, you can understand that this particular width is again controlled not just by the aspect ratio, but by the half angle parameter as well. And this is again reflected into the magnitude of change that the CME experiences. You can see that the width is now changing from a few tens to around 80 to 90 degrees. So that is almost double the change that we had observed in the age on widths. So the take-home message from this particular part is that once we are talking about widths, it's very important that what width are we talking about, or which perspective are we observing the CME from. Now that we have seen that the width of the CME is changing and the rate of change is also looking different in different heights, it is very much evident that the width of the CME will also influence the volume of the CME as a whole. Now, since the width is changing with different heights, we would also expect the volume to change. And to study that, what we do is we again go back to the schematic of the GCS generated schematic of the CME structure. And we can divide this GCS structure into three different parts. We can divide it into three parts, which is the top ellipsoidal leading front. And then we have this middle asymmetric disc. And then we have the pair of conical legs. So we can divide the entire CME structure into these three parts. And once we do that, we can do our own calculations. And based on the GCS recorded parameters, we can study the evolution of the volume of these three different structures separately and the whole CME as a whole. So once we do that, what we find something pretty interesting. What we see is, if you see the different data points in different colors are indicating the different sections of the CME body. So what we see is that different parts of the CME are actually expanding at different rates. So it seems that the CME is ceasing to act as a coherent structure. It seems that the leading front is following a completely higher exponent as far as the volume evolution is concerned. And this kind of tells us that probably there is a differential volume evolution inside the coronal mass ejections in the inner and outer corona. Also, I would like to draw your attention to this fact that the bottom two events which you see here, they are following much steeper power law. If you look at the power laws and compare them with the top three panels, you see that the bottom two events are following a steeper power law as respect to the other top three events. And we wanted to check why is that happening. Now, a basic look back into our calculations is what we found is—
Although you have to wind up in 2 minutes.
Sure, yeah. So what we found is the top three events were connected to active regions and the bottom two events were coming from this quiescent filament eruptions. And let me draw your attention to one of our earlier results, but which we had published in the last year, where we had showed that the width of the CMEs are following different power laws and that the CMEs coming from quiescent filaments are following a steeper power law. It seems that a similar trend is also getting followed in the volume evolution of the CME as well. And this is again claiming the role width of a CME plays as far as the volume evolution of the CME is concerned. So one of the ways to go ahead from here is, of course, is probably to study the face on and edge on widths of the CME and their distribution, and just find out whether there is a similar imprint of the source regions on that as well. Now, we also studied the evolution of the total volume of the CME, and we also found something fishy happening at around 4 solar radii. So what we found is there is a sudden change in the power law of the volume evolution of the CME happening at 4 solar radii. What we see is below 4 solar radii, the CME is following a much steeper power law, while beyond 4 solar radii, it is following an even flatter power law. So that tells you that these two different power laws is indicating towards the possibility that maybe the expansion mechanisms are different in the inner and outer corona. So also another important part is to appreciate the indivisibility of the inclusion of K-core observations, because that has offered us a good number of data points below 2 solar radii, and that has given us the luxury to differentiate between these two distinguishing behavior of the total volume evolution. If we didn't have observations below 2 solar radii, we wouldn't have been having the luxury or the confidence to segregate between these two behavior of the CME volumes at these two height regions. So to summarize, we have for the first time extended the application of the GCS model to K-core observations. And that has allowed us to track the CME with 3 vantage point tracking from a height as low as 1.1 solar radii. And this has again facilitated in capturing the impulsive acceleration phase and the perspective of width evolution from a face on and edge on point of view. We have also for the first time reported a power law behavior of CME volume with height, which has shown further that the different parts of the CME is kind of possibly following different expansion rates. We have also shown that the volume evolution is kind of following different power laws in the inner and outer corona, and hence possibility that the CME is possibly experiencing two different physical mechanisms as far as their volume evolution is concerned. Now, one of the major shortcomings or the limitations that we faced during this particular project is that we have ignored CME rotations, something which was discussed in the earlier talk, that and to have a proper handle on the rotation of a CME, we need observations above the ecliptic. So maybe including future data from future solar missions into the GCS model will again help us in understanding or having a better constraint understanding of the volume evolution by including rotational understandings. And also, since we have talked about separate volume evolution of the CME legs, I must also acknowledge that the identification of legs is pretty tricky, and it is only valid for CMEs with low aspect ratios, because CMEs with high aspect ratios, for them, the legs get smudged together, and it doesn't make sense to talk about the volume of the legs separately. You can go back to our paper for further details, and thank you so much for your attention.
Thank you, Satabdwa. And sorry, I mentioned your affiliation as Aries. Sorry about that.
No problem.
And there's time for only one question. So one who is very quick to ask a question already, Vagish. Yeah, please go ahead. Vagish, can you unmute yourself and ask?
Yeah, so Satabdwa, very nice talk, and I understand that it's a complex measurements and we need to be very precise. But my question is to your things which you mentioned in the introduction about the degeneracy. So actually you told that degeneracy should be in tilt angle and angular width, but I suspect that it should be in angular width and aspect ratio, because you are using face on width and edge on width. So can you comment on this?
Yeah, so the face on and edge on perspective is distinguished once you have the third vantage point, right? Not always you have this luxury that two vantage point gives you the distinction between these two orientations. So what I meant is, for the tilt angle, you have to first know the orientation of the neutral line. So that again, you can take it from the source region information, but again, that does not always give you a convincing evidence. So the best way to do it is from coronographic observations, maybe, as far as this particular model is concerned. And I feel that the degeneracy that I have experienced in these two parameters is solely happening mostly in the tilt angle, because if you have an edge-on view of the CME, both the viewpoints, let's say stereo A and stereo B gives you an edge-on view, then you cannot comment on the half angle parameter. You can just keep it 0 and you can maybe talk about tilt angle. That's what I feel.
The aspect ratios is more inherently linked to the angular width, right?
Yeah, but the tilt angle does not have a say on the aspect ratio, right?
Okay, so yeah, it's good work. We will discuss it sometime.
Sure, yeah.
Okay, thank you, Satabdwa. And I request all the participants, if they have questions for him, you can ask on the chat or go to Slack channel, as already mentioned on the chat. So we come to the end of this session of Sun and Solar System, and I thank all the speakers in this session for their very nice presentations, and all the audience for their questions and interactive discussion. Thank you very much. So if there are announcements from the local organizing committee, please.
Sorry,